Two galaxies drift toward each other across the void, their fates intertwined by forces beyond human scale. Billions of stars, each a potential solar system, drawn together in a slow-motion collision that reshapes the cosmos itself. This isn't science fiction. It's happening right now in the darkness between constellations, where galactic mergers unfold over epochs longer than civilization itself. But here's what most star charts won't show you. These cosmic collisions aren't random chaos. They follow a hidden blueprint, 44 precise mechanisms that dictate how galaxies tear apart, spiral together, and emerge reborn. Think of it as the universe's own playbook for reinvention, written in the language of gravity, dark matter, and starfire. And the most startling part: these silent dramas happening millions of light years away hold clues to our own Milky Way's future. Stick around, because by the time we're done, you'll never look at the night sky the same way again. Deep in the vast emptiness of space, gravity acts like an unseen hand, patiently pulling galaxies toward a shared destiny. This force, so familiar from our daily lives, works on scales so immense, entire galaxies bend to its will. Take our own Milky Way and the approaching Andromeda galaxy, for example. Right now, they're hurtling toward each other at roughly 400,000 kilometers per hour, locked in a gravitational embrace that began billions of years ago. What makes this dance so fascinating isn't just the sheer scale, but the details behind the pull. Density plays a crucial role. Regions packed with stars and dark matter exert a stronger tug than sparse outskirts. That's why galaxies don't just collide head-on like billiard balls. Instead, they spiral in gradually, their shapes distorting as gravity reshapes them. And dark matter, it's the hidden architect of this process, making up most of a galaxy's mass and dictating how strongly it attracts its neighbors. Einstein's insight into warped spacetime helps explain why this happens. Every galaxy sits in a sort of cosmic valley, a depression in the fabric of space created by its mass. When two galaxies come close enough, their valleys overlap, pulling them inexorably closer. Without this force, the universe would be a very different place. No grand mergers, no galactic evolution, just isolated islands drifting alone. But thanks to gravity, the cosmos is alive with motion, a stage set for some of the most breathtaking transformations in existence. Picture this: an invisible skeleton stretching far beyond the glittering arms of a spiral galaxy or the glowing core of an elliptical one. What we see through telescopes, the stars, the gas, the radiant nebulae, is merely the tip of the cosmic iceberg. The real action happens in the unseen realm of dark matter, a mysterious substance that doesn't emit, absorb, or reflect light, yet holds galaxies together like an unseen hand. Dark matter's influence becomes most apparent when galaxies begin their slow-motion tango toward one another. Long before their stars and dust clouds interact, their vast dark matter halos, colossal spheres of this enigmatic material, start overlapping, exerting an immense gravitational pull. Imagine two dancers feeling each other's presence long before they touch, their movements subtly adjusting in response. That's exactly how dark matter shapes a galactic merger, silently guiding every step of the process. Computer simulations reveal something extraordinary. Without dark matter, these mergers would play out very differently. Galaxies might pass right through each other, their stars too spread out to form lasting connections. But thanks to dark matter's gravitational grip, galaxies are drawn into intricate spirals, their structures warping and twisting as they merge. These halos act like cosmic glue, ensuring that when galaxies collide, they don't just fly apart. They reshape, merge, and evolve. And here's something even more fascinating. Dark matter doesn't just influence whether galaxies merge, it also determines how they merge. The size, density, and distribution of these halos dictate the speed of the collision, the angle at which galaxies approach, and even the final structure of the newly formed galaxy. Some mergers result in chaotic, irregular shapes, while others create stunning symmetrical spirals. The difference: dark matter's invisible blueprint. So next time you gaze up at the night sky, remember the most dramatic cosmic transformations aren't just about the stars we see. They're orchestrated by something we can't see, a force hidden in plain sight, shaping the universe in ways we're only beginning to understand. Now, let's zoom in on one of the most visually stunning aspects of galactic mergers, the immense, silent tug of war known as tidal forces. Think about how the moon's gravity stretches Earth's oceans, creating tides. Now, amplify that effect by billions. That's exactly what happens when galaxies draw near. Their gravitational pull doesn't just move stars, it warps the very fabric of these cosmic giants, bending their shapes into surreal, swirling distortions. Long before two galaxies fully collide, their outer layers begin stretching like taffy, forming vast, luminous arcs called tidal tails. Some of these tails span hundreds of thousands of light years, streaking across the void like celestial brushstrokes. And it's not just stars being pulled. Gas clouds get squeezed, triggering bursts of star formation. Suddenly, regions that once lay dormant ignite with newborn stars, turning quiet galactic outskirts into sparkling nurseries. The Milky Way and Andromeda are no exception. When they finally meet, their tidal forces will sculpt enormous, glittering bridges of stars between them. But here's the twist: this isn't destruction, it's transformation. The same forces that bend and twist galaxies also breathe new life into them, rearranging matter in ways that set the stage for their eventual rebirth. In fact, many of the most beautiful spiral galaxies we see today were shaped by these very forces, once distorted wrecks that settled into elegant new forms. So while tidal forces might seem violent, they're more like cosmic sculptors, reshaping galaxies in ways that are both destructive and creative. And the next time you look up at a particularly bright patch in the night sky, remember, you might be seeing the aftermath of an ancient galactic dance, where gravity didn't just tear things apart, but rebuilt them into something extraordinary. As two galaxies spiral toward each other in their gravitational embrace, an invisible force works behind the scenes, an intergalactic brake pedal silently slowing their dance. This cosmic deceleration isn't caused by empty space, but by something far more intriguing: countless stars and dark matter particles scattering like pinballs in the vastness between galaxies, stealing momentum with every indirect collision. Dynamical friction, the unsung architect of orderly mergers, doesn't work like everyday friction. There's no grinding or heat. Instead, imagine a celebrity trying to walk through a crowd. Each time someone turns to stare or follow, the celebrity loses a bit of forward energy. On a galactic scale, stars and dark matter act like that crowd, gravitationally reaching out as other stars pass by, subtly tugging them backward. Over millions of years, these tiny interactions add up, bleeding orbital energy until the galaxies can't resist falling closer together. Here's where it gets fascinating. Without this braking effect, galaxies might endlessly slingshot around each other like hyperactive children, never merging. But dynamical friction ensures a graceful spiral, transforming a potential cosmic traffic accident into a meticulously choreographed ballet. The larger the galaxy, the stronger this effect. Supergiant ellipticals can slow their partners down so efficiently that mergers unfold with surprising swiftness, at least by cosmic standards. What's truly remarkable is how this process leaves fingerprints. Astronomers can spot galaxies mid-merger precisely because dynamical friction distorts their shapes, stretching them into bizarre, elongated forms before they settle. And it's not just stars feeling the drag of dark matter halos. Those invisible scaffolds of galaxies experience it too, further shaping how the merger unfolds. So while gravity sets the stage, dynamical friction directs the performance, ensuring that when galaxies collide, they don't just crash. They converge, evolve, and ultimately create something entirely new. Among all the spectacular forces at work during a galactic merger, one of the most mesmerizing unfolds in what seems like near nothingness, the vast clouds of interstellar gas. Thin as it is, this diffuse material becomes the stage for a breathtaking cosmic ballet when galaxies collide. Unlike stars, which mostly glide past each other unharmed due to the immense distances between them, gas clouds crash headlong into one another, setting off chain reactions that light up the darkness. When two galaxies meet, their gas reservoirs slam together at staggering speeds, compressing under the force of the impact. The sudden pressure triggers violent shock waves, rippling through the clouds like pebbles dropped in a pond, except these waves span light years. Within these turbulent zones, pockets of gas grow dense enough to collapse under their own gravity, igniting thousands, sometimes millions of new stars in rapid succession. This phenomenon, called a starburst, transforms otherwise quiet galaxies into blazing beacons of star formation, visible across the universe, but the drama doesn't stop there. Some of this superheated gas doesn't form stars at all. Instead, it funnels toward the supermassive black holes lurking at the galaxy's cores. Like water spiraling down a drain, these infalling gas streams feed the black holes, turning them into voracious engines known as active galactic nuclei. The energy released in this process can outshine the rest of the galaxy combined, sending jets of radiation and particles shooting into space at near light speed. What makes gas hydrodynamics so fascinating is its dual nature. It's both a creator and a destroyer. The same shock waves that trigger starbirth also rip apart existing gas structures, scattering material across vast distances. Yet from this chaos emerges something new, a reshaped galaxy with freshly minted stars, energized black holes, and a future written in the swirling patterns of its remaining gas. Without this invisible fluid dance, galactic mergers would lack their most brilliant fireworks, and the universe would be a much darker, quieter place. When galaxies collide, they don't just rearrange stars, they ignite a celestial fireworks display unlike anything else in the universe. That's because the same gravitational chaos that twists and distorts galaxies also squeezes their vast reservoirs of gas with unimaginable force. And just like striking a match, that compression sparks a sudden, brilliant explosion of star birth. We're not talking about a few new stars here and there. During these collisions, galaxies can churn out hundreds, even thousands of stars every single year, transforming quiet cosmic neighborhoods into blazing stellar nurseries. For comparison, our own Milky Way typically forms maybe 1 or 2 stars annually during its quieter periods, but in the frenzy of a merger, that rate skyrockets, as if the universe itself has hit fast forward on creation. These starburst regions glow intensely, often outshining the rest of the galaxy. Young, massive stars, dozens of times larger than our sun, light up in vibrant blues and whites, their radiation ionizing surrounding gas into glowing nebulas. It's one of the rare times astronomers can actually watch galaxies change in real time, at least on cosmic scales, yet this dazzling spectacle comes at a cost. The very gas that fuels this star-forming frenzy gets used up at an unsustainable rate, like a wildfire burning through its fuel, which brings us to the bittersweet truth about these cosmic fireworks: they're spectacular, but fleeting. Within a few 100 million years, most of the available gas is either locked up in new stars or blown away by fierce stellar winds. The galaxy's burst of youth fades, leaving behind a population of young, hot stars that gradually cool and dim over eons. That's why recently merged galaxies often have a distinct blue tint, a telltale sign of recent, vigorous star formation. But here's the fascinating part. This cycle of boom and bust doesn't just light up the cosmos, it reshapes it. The starbursts during mergers seed galaxies with new stellar generations, mixing old and new stars in ways that determine the galaxy's fate. Some spiral galaxies we see today might owe their current structure to these ancient bursts of activity, their elegant arms forged in the chaos of collisions long past. So while the fireworks fade, their legacy burns on, written in the light of countless stars. At the heart of every merging galaxy lies an invisible predator, a supermassive black hole millions or even billions of times heavier than our Sun. These cosmic monsters don't just watch passively as their galaxies collide. They become active participants in the merger, locked in a slow but inevitable dance toward each other. As two galaxies spiral together, their central black holes, once separated by tens of thousands of light years, begin sinking toward the newly forming galactic core. Picture two heavyweight boxers circling each other in a ring, drawn together by forces neither can resist. But this isn't a quick fight. It's a cosmic tango that can take hundreds of millions of years, unfolding with such precision that astronomers can actually predict the steps. First, the black holes form a binary pair, whirling around each other in an ever-tightening orbit. Their immense gravity distorts the space around them, flinging nearby stars outward like a slingshot while consuming others. Yet even these voracious giants can't escape physics. Every time they interact with a passing star or gas cloud, they lose a sliver of energy, edging closer together. The final act, a collision of pure space-time disturbance. When they finally merge, their event horizons stretch, warp, and then violently snap together in a fraction of a second. The energy released in that instant is beyond comprehension, equivalent to millions of supernovae exploding at once, rippling through the universe as gravitational waves. These waves, first detected by scientists in 2015, carry the signature of black hole mergers happening billions of light years away, but the aftermath is just as fascinating. Rather than leaving destruction in their wake, the newly merged black hole stabilizes, becoming the anchor of the reshaped galaxy. Its gravity helps settle the chaos, sculpting the orbits of remaining stars and gas. Some theories even suggest these mergers are what create the most massive black holes in the universe, behemoths so large they defy conventional explanation. So while stars and gas paint the visible spectacle of galactic mergers, it's the black holes that write the final chapter, a violent yet strangely elegant finale to one of the universe's most dramatic transformations. Imagine two skaters spinning toward each other on a cosmic ice rink. Their speed, their angle of approach, even the way they twist their bodies all change how they'll collide. Galaxies operate by similar rules, carrying an invisible fingerprint of motion called angular momentum that dictates their fate during a merger. This isn't just about raw gravity or dark matter halos. It's about the spin, the innate rotation that gives each galaxy its unique rhythm in the grand dance of the cosmos. When galaxies merge, their angular momenta don't simply vanish. They combine, reshape, and redistribute like swirling water in a mixing bowl. If their spins align, reinforcing each other like perfectly synchronized dancers, the merger tends to produce a smooth, rounded elliptical galaxy. But if they clash spinning in opposing directions or at wild angles, the result is cosmic pandemonium, irregular, twisted structures that defy neat classification. The antennae galaxies, for instance, are locked in such a chaotic embrace, their conflicting spins stretching them into long, luminous tails of ejected stars and gas. Here's where things get even more fascinating. Angular momentum doesn't just determine the shape of the new galaxy, it also governs where stars and gas end up. Like a cosmic centrifuge, this spin flings material outward or pulls it inward, creating distinct zones of activity. Some gas gets hurled to the outer edges, forming glittering tidal tails, while other streams spiral toward the center, fueling bursts of star formation or feeding the waiting supermassive black hole. But the real marvel, this chaos isn't random. There's a hidden mathematics to it, a set of physical laws that ensure even the most violent mergers follow predictable patterns. Over time, gravitational interactions smooth out the turmoil, redistributing angular momentum until the galaxy finds a new equilibrium. What began as a clash of conflicting spins gradually settles sometimes into a stately elliptical galaxy, other times into a re-energized spiral with fresh, orderly arms. So while black holes and starbursts steal the spotlight in galactic mergers, never underestimate the quiet power of angular momentum. It's the silent choreographer of these cosmic collisions, ensuring that even in the universe's most chaotic moments, there's an elegance, a spinning, whirling order hidden just beneath the surface. As galaxies collide and new stars ignite with furious intensity, something extraordinary happens. The cosmos steps in with its own built-in thermostat. These aren't random explosions or unchecked chaos. They're part of a precise, self-regulating system known as feedback, where creation and destruction strike a delicate cosmic balance. Take those brilliant starbursts we see during mergers, the ones that churn out thousands of stars at once. Those young, massive stars don't just shine, they rage. Their intense radiation and powerful stellar winds act like galactic-scale blowtorches, pushing surrounding gas outward in vast shockwaves. This might seem destructive, but here's the twist. By clearing away excess gas, these winds actually prevent the galaxy from burning through its fuel too quickly. It's like a forest fire, creating firebreaks violent in the moment, but essential for long-term survival. Meanwhile, at the galaxy's core, another feedback mechanism kicks into gear. As supermassive black holes feast on infalling gas, they don't just grow quietly, they unleash devastating jets of energy, shooting particles at nearly the speed of light. These jets heat the surrounding gas to millions of degrees, making it too energetic to collapse and form new stars. At first glance, this seems counterintuitive. Why would a black hole suppress star formation? But that's the genius of feedback. It stops the galaxy from exhausting all its resources in one frenzied burst. Without these balancing acts, merged galaxies would face a grim fate, devouring their gas supplies in a few short million years, leaving behind a stagnant graveyard of aging stars. Instead, feedback ensures that star formation ebbs and flows in sustainable cycles, allowing galaxies to evolve without self-destructing. So while galactic mergers might look like pure chaos, there's an underlying rhythm, a push and pull between birth and restraint, that keeps these reborn galaxies thriving for billions of years. It's not just about how galaxies collide, but how they survive their own brilliance. While monumental collisions between galaxy titans grab headlines, there's another kind of merger happening constantly in the cosmic shadows. One so subtle you might miss it if you blinked across a few million years. These are minor mergers, where massive galaxies like our Milky Way quietly absorb their smaller neighbors, growing not through spectacular crashes, but through a patient accumulation of celestial crumbs. Unlike their dramatic counterparts, these events don't produce dazzling tidal tails or violent starbursts. Instead, they unfold like a slow-motion snowfall, each tiny galaxy dissolving into the larger one over eons, its stars blending seamlessly into the galactic halo. But don't mistake subtlety for insignificance. Over billions of years, these minor mergers act like cosmic masons, steadily adding mass, gas, and even entire star clusters to their host galaxies. Take the Milky Way's current dance with the Sagittarius Dwarf galaxy, a small satellite being torn apart by our galaxy's gravity. Right now, its stars streak across our skies in vast, faint streams, invisible to the naked eye but stunning through telescopes. This isn't some rare event, it's business as usual for a mature galaxy. In fact, astronomical evidence suggests our galaxy has already absorbed more than a dozen such dwarfs, their stars now part of the Milky Way's sprawling outer halo. Here's the quiet genius of minor mergers. While they lack the fireworks of major collisions, they bring fresh gas and raw materials that keep star formation simmering. Without these steady cosmic infusions, many galaxies would exhaust their fuel reserves and fade into stagnant old age. Instead, minor mergers provide just enough replenishment to sustain galactic life cycles without triggering violent disruptions. And that's not all. These interactions leave hidden fingerprints, slight distortions in a galaxy's outermost regions, unexpected star groupings, or even faint trails of dark matter. Studying them helps astronomers piece together a galaxy's history like detectives reading cosmic breadcrumbs. So while major mergers might steal the show, minor ones are the unsung architects, shaping galaxies one gentle assimilation at a time. Amid the chaos of colliding galaxies, an invisible thief lurks in the intergalactic shadows, stealing not stars or dark matter, but something far more precious, the lifeblood of star formation itself. This silent heist occurs through a process called ram pressure stripping, where the thin yet relentless currents of space itself wrench gas away from merging galaxies like leaves torn from a tree in a hurricane. Picture a galaxy moving through the sparse but pervasive material between galaxies, what astronomers call the intergalactic medium. Like a hand dragging through water, the galaxy feels resistance. But this isn't ordinary friction. It's a brutal force that can peel away entire reservoirs of gas, especially in crowded galactic neighborhoods like galaxy clusters. The denser the surrounding environment, the stronger the effect, with some galaxies losing their gas in mere millions of years. The consequences are dramatic. Without fresh gas to fuel new stars, a galaxy's vibrant spiral arms fade, its stellar nurseries shut down, and what was once a bustling hub of cosmic activity becomes a passive relic brimming with aging stars but devoid of new life. That's why we sometimes spot these red and dead galaxies drifting through clusters, their colors dulled by the absence of young, blue stars. Yet there's an intriguing twist to this cosmic robbery. While ram pressure strips gas from a galaxy's outer regions, the inner core often clings tightly to its reserves, leading to a strange duality where the galaxy's outskirts wither while its heart keeps forming stars. Some galaxies even leave behind glittering trails of stolen gas, marking their path like celestial breadcrumbs. What makes this mechanism especially fascinating is its reminder that galaxies don't evolve in isolation. They're shaped by their surroundings, by the push and pull of invisible intergalactic tides, by the density of their neighborhood, even by the ghosts of long-vanished mergers. So every time astronomers spot a gas-poor galaxy, they're not just seeing a victim of theft, they're reading a chapter in an epic, ever-unfolding story of cosmic survival. Deep in the densest neighborhoods of the cosmos, a slow-motion feast has been unfolding for billions of years, one where the largest galaxies grow even more massive by consuming their smaller neighbors. This isn't just happenstance, it's a fundamental rule of cosmic evolution called hierarchical merging, where size determines survival in the galactic food chain. Think of it as nature's way of ensuring the strongest structures endure, growing ever more dominant with each passing eon. The Milky Way is no innocent bystander in this process. Right now, our galaxy is digesting the remnants of at least a dozen smaller galaxies it has absorbed over its lifetime. Their stars now swirl in the faint halo surrounding our spiral disk, like celestial fossils whispering of ancient collisions. And this cosmic appetite isn't unique to us. The most enormous galaxies, like the supergiant ellipticals at the hearts of dense clusters, owe their immense size to countless mergers, each one adding mass and reshaping their structure. What makes galaxy cannibalism so crucial is how it mirrors the universe's growth on the grandest scales. Just as small streams merge to form rivers and rivers flow into oceans, galaxies assemble through successive mergers, building complexity over time. The largest galaxies didn't start out as titans, they grew incrementally, absorbing smaller systems in a relentless cycle that continues today. But here's the twist: the environment dictates the menu. In crowded galaxy clusters, where neighbors orbit close together, mergers happen frequently, producing behemoths with thousands of times more stars than the Milky Way. In sparser regions, galaxies tend to grow more slowly, feasting on only the occasional stray. This explains why the universe's true giants are almost always found in dense clusters. They're the product of an unbroken chain of cosmic consumption spanning billions of years. So while galaxy cannibalism might sound brutal, it's actually one of the key engines driving cosmic evolution. Every time a large galaxy absorbs a smaller one, it doesn't just grow, it inherits new stars, fresh gas, and sometimes even entire star clusters, enriching itself for the next chapter of its existence. The universe, it seems, has always operated on one simple principle: to grow, you must consume. When a galaxy goes into overdrive, birthing thousands of new stars in a fiery burst of cosmic productivity, it doesn't just light up the void, it unleashes something far more powerful. These starburst events create hurricane-like winds, roaring outward at speeds exceeding 2 million kilometers per hour. But these aren't ordinary gusts, they're galactic-scale tsunamis, powerful enough to blow entire reservoirs of star-forming gas clear out of the galaxy itself. What makes these outflows so remarkable isn't just their sheer force, it's what they carry with them. Heavy elements forged in the hearts of massive stars, carbon, oxygen, iron, get swept up in these winds and launched into intergalactic space. In a way, starburst-driven winds act like cosmic gardeners, scattering the ingredients for future stars and planets far beyond their home galaxy. Without them, the universe would lack the rich diversity of elements needed for rocky worlds, or even life itself. But there's a fascinating paradox at play. While these winds seem destructive, snuffing out star formation by removing the fuel, they're actually preserving the galaxy's future. By preventing the rapid, unsustainable consumption of gas, they ensure that star formation doesn't burn too bright and too fast. It's nature's way of hitting the pause button, cooling the galactic frenzy before it spirals out of control. Astronomers have spotted these winds in action, their telltale signatures written in the light of distant galaxies. Some outflows stretch for tens of thousands of light years, glowing faintly as they disperse into the void. Others collide with surrounding intergalactic material, creating shockwaves that ripple through the cosmic web. Far from being an endpoint, these winds are just another step in the cycle, a temporary exhalation before the galaxy draws breath again. So while mergers may trigger fireworks, starburst-driven winds ensure they don't consume the entire show in one dazzling burst. They're the universe's own balancing act, proof that even in chaos, there's a rhythm, a method to the celestial madness. Hidden within the chaos of colliding galaxies, an invisible scaffold weaves through the cosmic wreckage, threads of magnetism, so powerful they can steer entire rivers of interstellar gas. While gravity and dark matter dominate the grand architecture of mergers, magnetic fields act as the universe's silent conductors, orchestrating the flow of matter on scales that defy imagination. These fields don't just linger passively, they actively shape the drama. Picture a galaxy's magnetic lines like cosmic guardrails, channeling charged particles along precise paths. When two galaxies merge, their magnetic fields don't simply combine, they twist, knot, and sometimes amplify into immensely powerful structures. Gas surging toward the collision's core doesn't freefall randomly. It spirals along these magnetic highways, funneled toward star-forming regions or the gaping maw of supermassive black holes. Astronomers detect these ghostly fields through a clever trick, polarized light. As starlight passes through magnetized gas, its waves align in subtle patterns, like sunlight glinting off a rippling pond. By studying this polarization, scientists have mapped magnetic fields stretching across merging galaxies, revealing intricate webs that rival the complexity of their visible structures. Some fields even trace the phantom outlines of tidal tails, echoes of the merger's violence written in magnetism rather than stars. What's most surprising is how these fields persist in the frenzy. Turbulence from colliding gas should shred them apart, yet somehow they endure, reorganizing themselves like resilient spider silk. In rare cases, they even grow stronger, accelerating particles to near light speeds and creating brilliant synchrotron radiation, a telltale glow of electrons spiraling around magnetic lines. This all serves as a humbling reminder. The forces sculpting galaxies extend far beyond what telescopes can directly observe. While we marvel at the light of newborn stars or the fury of black holes, magnetism works in the shadows, unseen, relentless, and utterly indispensable to the cosmic order. At the heart of every spiral galaxy lies a dense, glowing nucleus, a concentrated hub of stars known as the galactic bulge. While the graceful spiral arms may be the galaxy's most photogenic feature, it's this central core that often proves most resilient when galaxies collide. Packed tightly with ancient stars, these bulges act like cosmic stabilizers, resisting the gravitational turmoil that twists and distorts their outer regions during a merger. Think of a galactic bulge like the keel of a ship, keeping the vessel steady even as waves crash against its sides. During a collision, while outer stars are flung into sweeping tidal tails and gas clouds are compressed into brilliant starbursts, the bulge often remains remarkably intact. Its sheer density gives it staying power. Stars here orbit so closely that gravity can't easily scatter them, allowing the core to maintain its structure even as the rest of the galaxy reshapes around it. But bulges aren't just passive survivors, they actively influence how mergers unfold. Their size and compactness determine whether the collision results in a chaotic mess or an orderly new galaxy. A large, tightly packed bulge can anchor the merger, acting as a gravitational pivot that steers incoming stars and gas into stable orbits. In contrast, a smaller or looser bulge might offer less resistance, leading to a more dramatic rearrangement of the galaxy's structure. And here's the twist: mergers don't just preserve bulges, they transform them. When two galaxies collide, their central bulges can merge into a single, more massive core, or in some cases, trigger processes that dissolve the bulge entirely, leaving behind a smoother, disk-dominated galaxy. Astronomers have even found pseudo-bulges, younger, disk-like structures formed by fresh waves of star birth during mergers, proof that these central hubs are far from static. By studying galactic bulges, scientists unlock clues about a galaxy's past collisions and its future evolution. Like cosmic time capsules, they preserve the history of mergers long after the outer chaos has settled, reminding us that even in the most violent galactic transformations, some structures endure reshaped but unbroken. The cosmic dance of galactic mergers isn't always a dramatic collision between equals. Sometimes it's a quiet, patient process, like a raindrop joining a river, barely causing a ripple yet still reshaping the current. This slow but relentless buildup, known as satellite accretion, sees massive galaxies steadily absorbing smaller neighbors, growing not through violent clashes but through gentle cosmic assimilation. While major mergers grab attention with their starbursts and tidal tails, satellite accretion works behind the scenes, methodically adding stars, gas, and even dark matter to its host galaxy. Picture a giant sequoia tree growing from countless fallen leaves. Each small addition might seem insignificant, but over billions of years, they contribute to something monumental. That's exactly how galaxies like our Milky Way have built their outer halos, where the remnants of past accretions still drift as faint stellar streams. One of the most stunning examples is the Sagittarius Dwarf spheroidal, a tiny galaxy caught in the Milky Way's gravitational pull. As we speak, it's being torn apart, its stars smearing across our skies in delicate, nearly invisible ribbons. Future astronomers might look back and see these streams as cosmic archaeology, clues to a long-absorbed companion, and Sagittarius is no outlier. Our galaxy's history is littered with such mergers, each leaving its ghostly fingerprint in the distribution of stars and dark matter. What makes satellite accretion so fascinating isn't just its subtlety, it's its inevitability. In dense galactic neighborhoods, smaller satellites have little chance of escape. Their orbits gradually decay, spiraling closer until the host galaxy's gravity peels them apart layer by layer. Unlike violent mergers, this process rarely triggers dramatic starbursts or active black holes. Instead, it's a gradual repurposing of material, a celestial recycling program on the grandest scale. Yet this slow feast has profound consequences. Each accretion tweaks the host galaxy's structure, sometimes thickening its disk, other times puffing up its halo. Even dark matter, invisible and elusive, gets redistributed in ways that subtly alter the galaxy's gravitational footprint. Over cosmic time, these tiny adjustments add up, helping shape the majestic spirals and stately ellipticals we see today. So while satellite accretion may lack the fireworks of its bigger siblings, It's just as vital to galactic evolution, a reminder that in the universe, even the quietest processes can leave echoes that last for eons. As the fireworks of a galactic merger fade, the tidal tails stretching into darkness, the starbursts dimming, a quieter but equally transformative phase begins. The newborn galaxy, still reeling from the collision, enters a period of cosmic reorganization so profound it rewrites its very structure. Astronomers call this violent relaxation, and despite the dramatic name, it's actually the universe's way of turning chaos back into order. Imagine shaking a snow globe with two distinct landscapes inside. At first, the pieces clash and tumble wildly, but as the flakes settle, they form an entirely new scene, one where the original details blur into something smoother, more unified. That's exactly what happens to stars and gas in a post-merger galaxy. Gravitational forces, no longer balanced by the galaxy's original rotation, pull everything into a new equilibrium. Orbits that were once neat and circular become randomized, like a crowd dispersing after a concert, until the system finds a fresh stability. This explains why merged galaxies often lose their spiral arms and delicate disks, instead becoming featureless ellipticals, celestial orbs of evenly distributed stars. The process isn't gentle. During violent relaxation, stars don't just drift into place, they're slingshotted by rapidly shifting gravitational fields, some flung outward while others plunge toward the core. Yet, paradoxically, this frenzy leads to harmony. Over hundreds of millions of years, the galaxy's structure smooths out, its light profile softening into the telltale glow of an elliptical. What's most remarkable is how efficient this cosmic reset button really is. Violent relaxation doesn't just redistribute stars, it erases evidence of the collision itself, wiping away the fingerprints of the original galaxies. Without it, merged systems might remain tangled wrecks forever. Instead, they mature into stately, symmetrical galaxies, their turbulent pasts visible only to the sharpest telescopes. So while mergers may steal the spotlight with their pyrotechnics, it's violent relaxation that writes the final act, an invisible hand sculpting chaos into a new kind of order, proving once again that even in the universe's most disruptive moments, balance always finds a way. After the cosmic fireworks of a galactic merger dim, something remarkable happens. The universe itself begins to exhale. Those searing clouds of gas, once superheated by violent collisions and starbursts, start a slow but transformative process of cooling. Like steam settling after a boiling kettle is turned off, this post-merger calm sets the stage for the galaxy's next act. Gas cooling isn't instantaneous, it's a meticulous cosmic chemistry experiment. The speed depends on two key factors: how tightly packed the gas is and how many heavy elements it contains. Denser regions cool faster as atoms collide more frequently, shedding energy like overheated engines radiating warmth. Meanwhile, metals elements heavier than hydrogen and helium act as microscopic radiators, efficiently releasing heat into space through complex atomic interactions. But the consequences couldn't be more dramatic. In galaxies where cooling happens rapidly, gas quickly condenses into dense, star-forming pockets, reigniting stellar birth like embers catching a fresh breeze. These galaxies stay vibrant, their disks shimmering with newborn stars. Yet when cooling lags, the gas remains too hot and diffused to collapse, leaving the galaxy in a kind of suspended animation, populated by aging stars but devoid of new ones. Astronomers see this divide across the cosmos. Some post-merger galaxies, buzzing with activity, owe their second wind to efficient cooling. Others, like the massive ellipticals at the hearts of galaxy clusters, languish as red and dead relics, their gas reservoirs too overheated by external pressures to ever properly cool. What's truly fascinating is how this process mirrors larger cosmic cycles. Just as Earth's climate shifts between ice ages and warming periods, galaxies oscillate between frenzied star formation and quiet dormancy, all dictated by the delicate balance of heating and cooling. The difference, for galaxies, the thermostat is forged in the aftermath of collisions, where the fate of billions of future stars hangs on something as simple as temperature. Galactic mergers don't always spell the end for delicate spiral arms. In a cosmic twist that defies expectations, some galaxies torn apart by collisions slowly reweave their spiral patterns, rising from the chaos like a phoenix with star-studded wings. This astonishing comeback, known as disk regrowth, proves that even the most violent mergers don't always lead to featureless ellipticals. Given enough time and the right conditions, a galaxy can reclaim its spiral grace. Take the case of a post-merger galaxy swimming in leftover gas. As the turbulence subsides, this material doesn't just linger, it gradually settles into a thin, rotating disk, drawn by the same physics that shapes raindrops into spheres. Angular momentum, that silent choreographer of cosmic motion, organizes the gas into orderly orbits, and where there's rotation, there's opportunity. Density waves ripple through the disk, compressing gas and dust into the familiar arcs of spiral arms. New stars ignite along these crests, their blue-white brilliance tracing out the galaxy's reborn silhouette. What's truly remarkable is how this process echoes across cosmic time. The Milky Way and Andromeda, destined to collide in about 4 billion years, might follow this very path. Rather than becoming a bland elliptical, their merger could eventually produce a new spiral one built from the ashes of two galaxies. Disk regrowth shatters the old assumption that mergers only move galaxies forward toward a dull, elliptical fate. Instead, it reveals galactic evolution as a dynamic cycle, destruction and rebirth on scales almost too vast to comprehend. So the next time you see a stately spiral galaxy, consider this. Its elegant arms might be the triumphant second act of a cosmic drama that began with a cataclysm. At the heart of merging galaxies, where swirling gas and newborn stars collide, something astonishing happens. A supermassive black hole awakens, not as a destroyer, but as a cosmic overseer. These gravitational behemoths, once thought to be mere devourers of matter, actually play a far more sophisticated role. When galaxies collide, the chaos sends torrents of gas spiraling toward their central black holes, igniting them into brilliant beacons known as active galactic nuclei, or AN. But instead of mindlessly consuming everything in sight, these AGN act like celestial regulators, releasing such immense energy that they can halt star formation across an entire galaxy. Think of it as the universe's ultimate balancing act. When a merger sends too much gas rushing toward the core, the AGN responds with jets of radiation and searing winds, blasting outward at nearly light speed. These forces don't just push gas around, they superheat it, making it too energetic to collapse into new stars. It's akin to holding a flamethrower to a snowstorm. The snowflakes don't stand a chance. And yet, this isn't destruction for its own sake. By preventing galaxies from burning through their fuel too quickly, AGN feedback ensures they don't exhaust their resources in a single, unsustainable burst. Scientists liken this process to a thermostat in a vast cosmic home. When star formation runs too hot, the AGN switches on, cooling things down. When things stabilize, the AGN quiets, allowing star birth to resume at a more measured pace. Without this self-regulation, galaxies could grow unchecked, ballooning into monstrous sizes that warp the cosmic landscape. Instead, AGN feedback keeps them in check, an unseen hand guiding galactic evolution toward equilibrium. The cosmic brilliance of this system lies in its timing. AGN activity peaks precisely when galaxies need it most, during and after mergers, when the influx of fresh gas could otherwise trigger runaway starbirth. Some of the most luminous objects in the universe, quasars, are actually AGN in this phase, shining brighter than 1,000 Milky Ways as they temper their galaxy's growth. And when their work is done, the galaxy isn't left barren, but balanced, ready for a new chapter of sustainable evolution. So while black holes might seem like the villains of the cosmos, their role in mergers reveals something far more nuanced. They're not just consuming, they're governing, ensuring that even in the chaos of collision, the universe maintains its perfect, delicate order. When galaxies collide, they don't just rearrange stars, they unleash tempests of unimaginable scale. Galactic winds, born from the fury of mergers, blast outward at speeds that dwarf hurricanes, carrying not just gas but the very building blocks of future worlds into the void between galaxies. These aren't gentle breezes, they're titanic outflows with enough force to reshape galactic ecosystems on a cosmic scale. At their core, these winds stem from explosive energy releases, supernova detonating by the thousands in starburst regions, or supermassive black holes spewing jets of searing plasma. The combined effect is like opening a pressure valve. Gas gets superheated and accelerated to millions of kilometers per hour, bursting through the galaxy's gravitational grip. But here's where it gets fascinating. These winds don't just take, they give. Heavy elements forged in stellar furnaces, carbon, silicon, iron, get swept up in the maelstrom, scattering far beyond their birthplace. This intergalactic seeding has profound implications. While the original galaxy loses fuel for future stars, nearby dwarf galaxies or even distant galaxy clusters might intercept these enriched winds, gaining precious materials to forge new generations of stars and planets. It's cosmic recycling at its grandest, one galaxy's sacrifice becoming another's opportunity. Yet galactic winds are nothing if not paradoxical. By expelling gas, they starve their home galaxy of star-forming material, effectively pressing pause on rapid growth. But this same deprivation prevents catastrophic overconsumption, allowing the galaxy to avoid burning through its reserves too quickly. Like a forest fire clearing underbrush, the destruction paves the way for healthier long-term growth. Astronomers spot these winds by their faint X-ray glow or the telltale spectral lines of displaced gas stretching across millions of light years. Some outflows even leave behind vast, magnetized bubbles, ghostly remnants of their passage through intergalactic space. So while mergers might seem like self-contained events, their winds stretch far beyond, threading the cosmos with the ingredients for new beginnings. What one galaxy loses becomes the universe's gain, proof that even in expulsion, there's evolution. Amid the gravitational wreckage of colliding galaxies, something extraordinary defies the odds, brand new galaxies being born from the chaos. These aren't ancient relics, but cosmic infants, tidal dwarf galaxies, forged in the violence of mergers and left to chart their own path through the universe. While most mergers tear structures apart, tidal forces can also create. Picture two galaxies whipping past each other, their gravitational pull stretching vast streams of gas and stars into elongated tails. Normally, this material might scatter into oblivion, but sometimes, if the conditions are just right, pockets of debris collapse under their own gravity, condensing into fully fledged dwarf galaxies. It's like watching a storm surge carve out a new island, only on a scale so vast it defies imagination. What makes these tidal dwarfs so fascinating isn't just their origin, but their chemistry. Unlike primordial dwarf galaxies, which formed in the early universe and are dominated by lightweight elements, tidal dwarfs inherit enriched material from their parent galaxies. Their stars and gas carry traces of heavier elements forged in supernova and stellar winds, making them distinct cosmic fingerprints of the collisions that birthed them. But here's the real twist. These accidental galaxies aren't just cosmic curiosities. They serve as living records of the mergers that created them. By studying their orbits and composition, astronomers can reconstruct the trajectories and forces at play during the collision, like forensic scientists piecing together a celestial crime scene. Some tidal dwarfs even retain faint echoes of their parents' spiral patterns, frozen in time like echoes of a vanished past, and their survivors, though born from chaos, many tidal dwarfs endure for billions of years, orbiting their parent galaxies as silent witnesses to ancient cataclysms. Others drift free, carrying the legacy of their violent births into the wider cosmos. So while mergers may tear galaxies apart, they also stitch new ones together, proof that in the universe, even destruction can spark creation. As galaxies merge and settle into their new forms, they leave behind more than just reshaped structures. They scatter celestial breadcrumbs across the cosmos. Among these lingering traces, none are more hauntingly beautiful than star streams, delicate ribbons of stars winding through galactic halos like threads of cosmic embroidery. These aren't random scatterings. They're the unraveled remains of galaxies long since consumed, their stars dragged into elongated orbits that betray their violent origins. Take a closer look at the Milky Way's halo, and you'll find these ghostly signatures everywhere. The Sagittarius stream, for instance, arcs across our skies like a faded scar, the lingering remnant of a dwarf galaxy torn apart by our own over billions of years. Then there's Gaia's Enceladus, an even older stream whose stars tell the story of a colossal merger that reshaped our galaxy in its youth. Each of these streams is a fossilized record, preserving the chemistry, motion, and even the timing of ancient collisions. What makes star streams so valuable to astronomers isn't just their history, it's their predictability. Unlike rogue stars or chaotic clusters, these streams follow precise orbital paths dictated by gravity. Track their movements, and you're essentially rewinding a cosmic film, uncovering not just how galaxies merged, but when, how violently, and even what their original shapes might have been. Some streams are still fresh, their stars barely dispersed. Others are so stretched and faded they're nearly invisible, detectable only through their subtle gravitational whispers. Yet these streams are more than just relics, they're active participants in galactic evolution. As they loop around their host galaxies, their gravity subtly tugs on nearby gas and dark matter, warping the very fabric of their new home. Over time, their stars will fully blend into the galactic halo, their stories erased, but for now, they linger as celestial storytellers, whispering secrets of the universe's unending dance of destruction and renewal. Long before galaxies collide in dramatic mergers, they frequently engage in an elegant celestial courtship, locking into mutual orbits that can last longer than Earth has existed. These galactic pairs, sometimes called binary galaxies, represent the universe's slow-motion overture to a merger, where gravity begins its subtle work of distortion long before the final embrace. Unlike solitary galaxies drifting through the void, paired systems are bound together by their mutual gravity, tracing vast elliptical paths around a shared center of mass. The distances between them might seem enormous, tens or hundreds of thousands of light years, but over cosmic time, even these gaps narrow. With each orbit, tidal forces gently stretch their structures, pulling wisps of stars and gas outward into faint bridges or distorting their spiral arms. It's like watching two dancers circling each other, their movements gradually synchronizing as they prepare for the final act. What makes these pairs so invaluable is their ability to reveal the early stages of a process that normally unfolds too slowly to observe. By studying systems like the famous Whirlpool Galaxy and its companion NGC 5195, astronomers witness how gravity redistributes material long before a full merger. Some pairs even exhibit starburst rings, where gas compressed by their mutual pull ignites frenzied star formation, a preview of the fireworks to come. But timing is everything. Depending on their mass, trajectory, and surroundings, some binary galaxies may spiral together within a few billion years, while others remain locked in their dance indefinitely. Their fate hinges on factors like dynamical friction, that cosmic brake pedal we discussed earlier, which steadily drains their orbital energy until collision becomes inevitable. For scientists, these pairs are more than just celestial snapshots. They're time capsules preserving the prelude to galactic transformation. By mapping their interactions, researchers can reconstruct the Milky Way's own future encounter with Andromeda, predicting not just when they'll merge, but how their structures will warp in the process. So while mergers dominate the headlines, it's often these quiet, enduring partnerships that hold the keys to understanding the universe's grandest rearrangements. Even in the crowded cosmos, galaxies don't always collide. Sometimes they just pass each other by, like ships in the cosmic night. These fleeting encounters, known as flyby interactions, prove that near misses can be just as transformative as direct mergers. Without ever fully committing, galaxies still leave lasting marks on one another, stretching spiral arms, igniting bursts of starbirth, and stealing wisps of gas without looking back. What's fascinating is how delicate these gravitational brushes can be. As two galaxies glide past each other, their mutual pull warps their shapes like hands pressing on opposite sides of a balloon. The iconic Whirlpool Galaxy, for example, owes its sweeping spiral arms not to a full merger, but to a close shave with a smaller companion. These distortions aren't just cosmetic, they compress gas clouds, sparking waves of star formation that might otherwise have slept for eons. But the real intrigue lies in what gets left behind. Just as a gust of wind can strip leaves from a tree, flybys use gravitational forces to pluck gas from a galaxy's outskirts. Some of this stolen material trails behind in faint, glowing bridges, while the rest disperses into the void, fuel lost for future stars. And here's the twist. Unlike the all-consuming nature of mergers, flybys allow galaxies to keep most of their identity intact, altered but not obliterated. These near misses also serve as cosmic reminders. Not all interactions lead to mergers, but all interactions leave a trace. From the faintest distortion to the brightest starburst, galaxies carry these fleeting encounters in their structure long after the moment has passed. So while mergers may dominate the headlines, flybys quietly shape the universe in their own subtle way, proving that even a glancing blow can ripple across galaxies for billions of years. 26th mechanism, galaxy harassment, the slow distortion. Not every galaxy faces a single, catastrophic collision. Some endure a subtler, more relentless fate. In the dense neighborhoods of galaxy clusters, where cosmic traffic runs high, individual galaxies never get a moment's peace. Instead of one dramatic merger, they suffer galaxy harassment, a slow, persistent pummeling from countless gravitational encounters that warp and whittle them down over billions of years. Picture a lone ship navigating a stormy sea, buffeted by wave after wave. Each hit might seem minor, but over time, the constant battering takes a toll. That's exactly what happens to galaxies trapped in crowded clusters. Every close pass with another galaxy, every gravitational tug, no matter how slight, chips away at their structure. Spiral arms fray, delicate gas reservoirs get stripped, and even the orbits of stars are nudged out of alignment. Unlike a sudden merger, which reshapes galaxies in a blaze of starbursts and tidal tails, harassment works in whispers, eroding them bit by bit until they're almost unrecognizable. What makes this process so insidious is how it targets the very lifeblood of galaxies, their gas. Without it, star formation grinds to a halt, turning vibrant spirals into faded, aging relics. And because these interactions happen so often in clusters, harassed galaxies rarely get a chance to recover. They're caught in an inescapable cosmic grind, their transformations playing out in slow motion across eons. Yet there's a strange beauty to this gradual metamorphosis. The harassed galaxies that survive often evolve into lenticular forms, neither fully spiral nor elliptical, but something in between. Their disks remain intact, though stripped of active star-making material, while their bulges grow more pronounced. They become galactic phantoms, echoes of what they once were, sculpted not by a single defining event, but by the accumulated wear and tear of a crowded universe. So while galaxy harassment might lack the fireworks of a full merger, its effects are just as profound. It's a reminder that in the cosmos, destruction isn't always sudden sometimes. It's the slow, unrelenting pressure of time and environment that reshapes the universe, one subtle encounter at a time. In the vast cosmic arena, where galaxies collide like celestial titans, there exists an even grander spectacle: the merging of galaxy clusters themselves. These behemoth gatherings, each containing hundreds or even thousands of galaxies, represent the largest gravitationally bound structures in the universe. And when they collide, the sheer scale of destruction and transformation defies comprehension. Unlike individual galaxy mergers, cluster mergers unfold on a stage spanning millions of light years. Picture two immense cosmic metropolises, each a swirling tapestry of galaxies, dark matter, and superheated gas, plunging toward each other in a slow-motion train wreck. The gravitational forces at play here are so immense that they don't just warp galaxies, they bend the very fabric of space-time in their vicinity. The aftermath is nothing short of cataclysmic. As the clusters intersect, their colossal gas clouds slam together at thousands of kilometers per second, generating shock waves that reverberate through intergalactic space. These shocks heat the gas to temperatures exceeding tens of millions of degrees, making it glow fiercely in X-rays visible only to space telescopes designed to capture such extreme energies. Meanwhile, magnetic fields tangled in the chaos accelerate particles to near light speed, creating vast, invisible rivers of cosmic rays that streak across the universe. Yet amid this cosmic bedlam, something remarkable happens. The galaxies within these clusters, oddly enough, barely notice the chaos. Like ships sailing through a hurricane, they pass through unscathed, their stars so widely spaced that direct collisions are nearly impossible. Instead, they're carried along by the gravitational tides, their trajectories altered but their structures largely intact. It's the diffuse gas and dark matter that bear the brunt of the collision, sculpting the final shape of the new, even larger supercluster. For astronomers, these mergers are more than just displays of cosmic power, they're invaluable laboratories. By studying the way clusters collide, scientists can trace the distribution of dark matter, measure the universe's expansion rate, and even probe the nature of gravity itself. Some of the most massive structures we've discovered, like the Bullet Cluster, serve as ghostly imprints of these ancient battles, revealing dark matter's presence through the way it bends light. So while galaxies may be the stars of most cosmic collision stories, cluster mergers remind us that the universe operates on scales even more staggering, where entire galactic cities are reshaped in events so immense, they redefine our understanding of space itself. Here's the next part of the script, following your guidelines. 28th mechanism, gas depletion, the end of star formation. Galaxies thrive on gas. It's the raw material for stars, the fuel that keeps their engines burning bright. But when galaxies merge, this vital resource doesn't just get used up, it gets obliterated. Some gas becomes stars in spectacular bursts, while the rest is hurled into deep space, leaving behind a galaxy that's literally running on empty. The result, a celestial retirement home where aging stars glow red and dim, and new ones simply aren't born anymore. Think of it like a wildfire raging through a forest. At first, the flames consume everything in a brilliant, all-consuming rush, countless stars igniting in a frenzy. But once the fire burns out, only embers remain. That's exactly what happens in gas-depleted galaxies. The brilliant starbursts of a merger leave behind a wasteland, where the last generations of stars slowly cool into oblivion. But why does this happen so dramatically in mergers? It's a perfect storm of destruction. Collisions compress gas clouds, triggering runaway star formation that burns through reserves at breakneck speed. At the same time, shockwaves from supernova and black hole winds blast away any remaining gas, like a cosmic hurricane stripping a landscape bare. The galaxy isn't just starved, it's sterilized, cut off from the very thing that could rejuvenate it. Astronomers call these galaxies red and dead, their light dominated by older, cooler stars, their spiral arms faded into smooth, ruddy glows. Some of the most massive galaxies in the universe, like the giant ellipticals at cluster centers, are in this state, monuments to ancient collisions that left them barren. Yet this isn't the end of the story. Gas depletion doesn't mean total oblivion, it's just a new phase. These galaxies might one day be reignited if they capture fresh gas from intergalactic space or merge with a gas-rich neighbor. Until then, they stand as cosmic cautionary tales, proof that even the brightest fires can burn out, and that in the universe, no feast lasts forever. This segment keeps the tone engaging and varied while exploring the concept clearly, making it accessible without sacrificing depth. Let me know if you'd like any refinements. 29th mechanism, metallicity changes cosmic chemistry. Galactic mergers don't just reshape stars and gas, they rewrite a galaxy's very DNA. Hidden in the light of every star lies a chemical fingerprint, a record of the elements forged in cosmic furnaces. When galaxies collide, their distinct chemistries blend like ingredients in a celestial mixing bowl, creating entirely new stellar generations with compositions unlike anything that came before. This cosmic alchemy hinges on metallicity, the abundance of elements heavier than hydrogen and helium. Older stars, born in the pristine early universe, are metal poor, forged from nearly pure primordial gas. Younger stars, like our Sun, carry traces of heavier elements carbon, oxygen, iron synthesized in previous stellar explosions. But when galaxies merge, their gas clouds, each with its own unique metallicity, crash together, scrambling these chemical signatures. The resulting stars inherit this mixed chemistry, becoming living archives of the collision. Astronomers decode these fingerprints through spectroscopy, splitting starlight into rainbows that reveal absorption lines, dark gaps where specific elements absorb light. In post-merger galaxies, stellar spectra often show abrupt metallicity shifts, exposing populations of stars with wildly different origins now orbiting side by side. Some clusters might bear the high metallity imprint of a gas-rich spiral, while others retain the metal, poor legacy of a dwarf galaxy consumed long ago. But here's where it gets truly fascinating. These chemical changes aren't just historical records. They shape the galaxy's future. Metals act as cosmic coolants, helping gas condense into new stars more efficiently. A sudden influx of enriched material from a merger can ignite star formation in ways pure hydrogen never could. Conversely, metal-poor gas might linger dormant until stirred by a collision. So while tidal tails and starbursts fade, metallicity shifts endure, etched into the stars themselves. Long after the fireworks of a merger dim, its chemical legacy burns on. Proof that in the cosmos, even destruction leaves behind the building blocks of something new. 30th mechanism. Galaxy transformation spirals to ellipticals. The universe has a way of turning elegance into efficiency. Take spiral galaxies, those majestic, star-filled whirlpools with delicate arms and sleek disks. When two of them collide, gravity doesn't just reshape them, it reinvents them, forging something entirely new from the wreckage. What starts as a graceful dance ends with a cosmic metamorphosis, the birth of an elliptical galaxy. Unlike spirals, ellipticals are smooth, featureless orbs of stars. No sweeping arms, no delicate disks. Their stars don't orbit in neat, organized planes but move in all directions, as if the galaxy itself can't decide which way to spin. This transformation isn't just cosmetic, it's a fundamental restructuring of an entire galactic ecosystem, rewriting the rules of how stars move and interact. So how does a meticulously ordered spiral become this randomized cosmic sphere? The answer lies in the chaos of collision. When two galaxies merge, their gravitational tides yank stars from their original orbits, hurling them in unpredictable directions. Imagine shaking a snow globe so violently that every flake scatters except here. The flakes are billions of stars, each sent careening along a new path. Over time, this gravitational jostling smooths the galaxy into a rounded shape, erasing any trace of its once pristine spiral arms. But ellipticals aren't just shapeless blobs. They are relics of ancient violence. Some are compact, packing stars tightly like celestial snowballs. Others stretch into elongated footballs, their forms warped by the angle of their original collision. The largest ellipticals, often found at the hearts of galaxy clusters, are the ultimate mergers, monsters built from countless galactic assimilations over billions of years. Yet there's a strange beauty to this transformation. While spirals symbolize cosmic order, ellipticals embody resilience, proof that even the most chaotic disruptions can lead to new forms of stability. Their stars might move in disorderly orbits, but they're no less permanent, no less vital. The universe doesn't destroy without rebuilding, and in the grand galactic workshop, even collisions carry a purpose, turning the delicate into the durable, one merger at a time. 31st mechanism. Ring galaxies, the bullseye effect amid the chaos of galactic collisions, nature occasionally produces something astonishingly precise, a perfect cosmic bullseye. Ring galaxies, with their symmetrical, jewel-like bands of stars and gas, stand out as some of the most breathtaking anomalies in the universe. Unlike the tangled wreckage of most mergers, these structures emerge when a smaller galaxy spears directly through the heart of a larger spiral, sending ripples of star formation cascading outward in a near-perfect circle. The physics behind this phenomenon is as elegant as the result. When an intruder galaxy plunges through the disk of a larger one, it doesn't just scatter stars, it compresses the gas like a stone dropped in a pond. The shockwave races outward, triggering a sudden burst of star formation along an expanding ring. Meanwhile, the galaxy's center, jolted by the impact, often remains eerily undisturbed, creating the illusion of a celestial target. Take the Cartwheel Galaxy, one of the most famous examples. Its brilliant blue ring, over 150,000 light-years across, glows with the light of countless newborn stars, all sparked by a smaller galaxy's piercing collision millions of years ago. What's remarkable isn't just the ring itself but the aftermath. The intruder galaxy, having done its work, often escapes relatively unharmed, leaving behind a transformed masterpiece. Ring galaxies are more than just cosmic oddities, they're living laboratories. Their symmetrical structure lets astronomers study shock waves, star formation, and gas dynamics with unusual clarity. And because these events are so rare, making up less than 1 in 1,000 known galaxies, each discovery offers fresh insights into how gravity and chaos can conspire to create something unexpectedly beautiful. So while most mergers leave behind tangled wrecks or featureless ellipticals, ring galaxies remind us that destruction can sometimes yield precision. In the grand celestial workshop, even a violent collision can produce artistry, a fleeting glimpse of order carved from chaos. 30-second mechanism, polar ring galaxies, the cosmic oddballs imagine a galaxy spinning gracefully through space only to have another galaxy crash into it at a right angle, leaving behind a cosmic carousel of stars whirling on a completely different plane. This bizarre phenomenon creates polar ring galaxies, celestial anomalies where a bright band of gas, dust, and stars orbits perpendicular to the main galaxy's disk, like a hula hoop around a spinning top. Most galactic collisions happen along roughly aligned planes, preserving some sense of order. But when a smaller galaxy swoops in edge-on nearly sideways relative to the larger one, gravity can rip it apart, scattering its remains into a polar orbit. The result defies expectations. A galaxy with two distinct rotation axes at odds with each other, challenging everything we know about angular momentum. Take NGC 660, one of the most striking polar ring galaxies known. Its tilted ring, packed with young blue stars and glowing gas, stands in stark contrast to the older, yellower stars of its central disk. This isn't just a visual oddity, it's a gravitational puzzle. How can such a structure remain stable when physics says it should collapse or realign? The answer lies in the delicate balance of forces. The ring's material orbits just fast enough to resist collapsing into the main disk, yet not so fast that it flies apart, a cosmic tightrope act that can last billions of years. Astronomers suspect these rare configurations might be galactic snapshots, capturing a fleeting phase in merger evolution. Over time, the ring could gradually settle into the main disk, or, if conditions are right, persist as a long-lived anomaly. Either way, polar ring galaxies force us to rethink the rules. They prove that mergers don't always follow the script. Sometimes they rewrite it entirely, leaving behind structures so strange they stretch our understanding of the universe itself. So while most collisions smooth galaxies into familiar shapes, polar rings remind us that chaos can also create the unexpected celestial oddities spinning defiantly against the tide. 33rd mechanism. Shell galaxies. Layers of history. Peel back the layers of certain galaxies, and you'll uncover something astonishing: delicate, nested arcs of stars, stacked like celestial onions. These shell galaxies aren't just cosmic oddities, they're stellar archives, preserving the aftermath of collisions in ways no other structure can. When a smaller galaxy plunges into a larger one at just the right angle, it doesn't just blend in, it splashes, sending ripples of stars outward until they freeze in place, suspended in concentric rings. The physics behind these shells is as mesmerizing as their appearance. As the victim galaxy gets torn apart, its stars don't scatter randomly. Instead, they follow precise gravitational rhythms, bunching up at specific distances from the core, like waves cresting at fixed intervals. Over time, these starry layers settle into eerie stillness, creating the illusion of a galactic art installation. NGC 3923, one of the most striking examples, boasts over 20 distinct shells, each a snapshot of the violence that shaped it. What makes these structures so invaluable is their clarity. Unlike messy tidal tails or distorted spirals, shells map the merger's history with near mathematical precision. Their spacing reveals the speed of the collision, their symmetry hints at the angle of impact. Some even show gaps where the intruder galaxy lost chunks of material mid-fall, cosmic breadcrumbs leading back to the event itself. Yet there's a haunting beauty to their stillness. These shells don't flicker with newborn stars or blaze with active black holes. They're relics, frozen in time, ghostly echoes of a long-ago cataclysm that reshaped two galaxies into one. And as astronomers decode their patterns, they're finding something even more profound: proof that destruction, when viewed across cosmic timescales, can be as methodical as it is violent, a sculptor chiseling history into the stars. 34th mechanism. Ultra-luminous infrared galaxies. Cosmic powerhouses in disguise. Some of the universe's most violent collisions don't blaze across the cosmos in visible light. They smolder behind thick veils of dust, radiating an eerie glow in the infrared. These are ultra-luminous infrared galaxies, or ULERG, cosmic monsters so energetic they outshine entire galaxies, yet remain nearly invisible to traditional telescopes. Behind their obscuring curtains of dust, titanic forces rage. Starbursts churn out stars at breakneck speed, while supermassive black holes feast on swirling gas, their combined energy funneled into heat rather than light. What makes ULERG so extraordinary isn't just their luminosity, it's their origin story. Almost all are galaxies caught in the throes of a merger, their collision compressing gas and dust into dense, chaotic regions. As gravity tightens its grip, these clouds collapse into newborn stars at rates hundreds of times faster than in ordinary galaxies. Meanwhile, vast quantities of dust absorb nearly all the visible light these stars produce, re-radiating it as infrared, a thermal footprint of the bedlam within. Peering through the dust with infrared telescopes reveals the true scale of the frenzy. Take ARP 220, one of the closest ULERG, though it looks like a single blurry smudge in visible light. Infrared imaging unveils twin galactic cores, each blazing with star formation and active black holes, separated by just 200 light-years, a telltale sign of two galaxies merging into one. The energy released here is almost incomprehensible, trillions of times brighter than our sun, yet hidden behind walls of cosmic debris. But ULERG aren't just spectacular oddities. They're cosmic beacons signaling a critical phase in galactic evolution. Many astronomers believe these dust-choked giants are the precursors to elliptical galaxies, their furious starbursts and black hole activity eventually blowing away the obscuring material, leaving behind a red and dead remnant. Others may evolve into quasars, their central black holes emerging from the dust to dominate the scene. These hidden titans remind us that the universe's most dramatic transformations often happen unseen, shrouded in the very chaos they create. While optical telescopes show us the calm aftermath of mergers, infrared eyes reveal the inferno hidden beneath, proving that sometimes the brightest cosmic fireworks are the ones we can't even see. 35th mechanism, dwarf galaxy disruption, the silent demise. Not all galactic endings are violent spectacles. Some fade away with barely a whisper. While massive mergers light up the cosmos with starbursts and tidal tails, dwarf galaxies meet their fate in near silence. These cosmic minnows, drawn into the gravitational pull of larger galaxies, don't collide so much as dissolve. Their stars gently stripped away and scattered into the halo, like sand castles melting into the tide. What makes dwarf disruption so elusive is its subtlety. Unlike dramatic mergers, which leave behind glowing debris fields or distorted shapes, this process unfolds with eerie neatness. The dwarf stars don't collide or ignite, they simply drift apart, mingling with the host galaxy's halo in a dispersion so smooth it's nearly invisible. Even the most powerful telescopes struggle to trace the remnants, as these orphaned stars blend seamlessly into the galactic background, yet their disappearance leaves hidden clues. By mapping the motions and compositions of stars in galactic halos, astronomers uncover stellar streams, faint, river-like traces of stars moving in unison. These are the ghosts of devoured dwarfs, their former structures erased but their orbital paths still betraying their origins. The Milky Way's halo, for instance, is littered with such relics, each stream a fossilized record of a long-vanished neighbor. The quiet efficiency of this process reveals something profound about galactic evolution. While titanic mergers build galaxies up, dwarf disruption fills in the gaps, steadily contributing stars, dark matter, and even globular clusters to their larger hosts. It's cosmic recycling at its most discreet, a reminder that in the grand narrative of the universe, even the smallest actors leave an enduring mark. So next time you gaze at a majestic spiral or a gleaming elliptical galaxy, remember, its splendor may owe as much to these silent assimilations as to any headline-grabbing collision. The universe doesn't just grow through fireworks sometimes, it expands one nearly invisible act of dissolution at a time. 36th mechanism, galaxy thickening disks puff up. Picture a sleek, spinning dinner plate, smooth, thin, perfectly balanced. Now imagine someone bumping the table, sending the plate wobbling as its edges rise and warp. That's precisely what happens to galaxies during mergers, except on a scale so vast, it reshapes the fate of billions of stars. When galaxies collide, their once flat disks don't just bend, they inflate, transforming orderly spirals into puffed-up hybrids that blur the line between disk and elliptical galaxies. This cosmic thickening happens as stellar orbits, once neatly aligned like cars on a racetrack, get jostled into chaos. Imagine two sheets of stars sliding past each other, their gravitational tug-of-war yanks stars upward and downward, scattering them into a broader, puffier disk. Over time, these disrupted orbits settle into a new equilibrium, no longer confined to a thin plane, but instead filling a thicker, almost barrel-shaped region. Our own Milky Way bears the scars of this process. Its thick disk, a layer of older stars stretching far above and below the main spiral, is likely the fossilized imprint of ancient minor mergers stirring up the galactic mix. What makes this mechanism so fascinating isn't just the structural change, it's the subtle way mergers rewrite a galaxy's identity. A thin, delicate spiral might emerge from a collision with a slightly thickened profile, its stars now moving in more randomized paths. Some galaxies end up caught in a cosmic identity crisis too structured to be true ellipticals, yet too puffed up to remain classic spirals. It's a reminder that galactic evolution isn't always a one-way street. Sometimes it's a series of careful adjustments, each collision leaving behind a trace in the star's motions. And here's the twist: thickening doesn't just alter a galaxy's appearance, it changes its future. A puffed-up disk cools more efficiently, potentially slowing future star formation. Its stars, now traveling on wider paths, interact differently with dark matter halos and nearby gas clouds. Even the galaxy's lifespan might stretch longer, its thickened structure more resistant to further disruptions. So while tidal tails and starbursts grab the spotlight, disk thickening works in the background, an unsung architect of galactic form. Every time we spot a galaxy with an unusually robust profile, we're likely seeing the quiet aftermath of a cosmic encounter, where chaos didn't destroy order but simply reshaped it into something new. 37th mechanism. Counter-rotating disks spin reversal. Most galaxies spin with a single, unified rhythm, a cosmic waltz where stars and gas move together in harmony. But sometimes, mergers throw that rhythm into disarray, creating something extraordinary. A galaxy where two disks of material spin against each other, like gears grinding in opposite directions. These counter-rotating disks are cosmic anomalies, rare, mesmerizing, and a testament to how mergers can rewrite a galaxy's very motion. Here's how it happens. When two galaxies collide, their gas doesn't always blend seamlessly. If one galaxy's gas arrives on a skewed trajectory, perhaps from a near miss or a glancing blow, it can settle into a new disk that spins backward relative to the original. Picture pouring cream into a swirling cup of coffee. If you pour just right, the cream might briefly form its own tiny whirlpool, spinning the opposite way. On a galactic scale, that fleeting effect becomes frozen in time, locked into the galaxy's structure for billions of years. NGC 4550, a galaxy in the Virgo cluster, offers a stunning example. Observations reveal two distinct populations of stars orbiting in opposite directions, half spinning clockwise, the other half counterclockwise. This isn't just a quirk, it's a fingerprint of past violence, a sign that NGC 4550 likely absorbed another galaxy whose angular momentum was flipped during the encounter. Counter-rotating disks do more than just defy expectations, they challenge galactic stability. Stars and gas moving in opposite directions experience extra-gravitational drag, like swimmers fighting against a current. Over cosmic time, this friction can heat the disk, puffing it up or even funneling gas toward the central black hole, reigniting activity in an otherwise quiet core. Yet these cosmic contradictions also hold clues. By studying them, astronomers trace the history of mergers too subtle to leave tidal tails or starbursts. A backward spinning disk might be the only visible relic of a long-ago collision that otherwise faded into the galactic background. So while most mergers blend motion into a unified flow, counter-rotating disks remind us that chaos lingers in the details, a silent, spinning rebellion etched into the stars. 38th mechanism, galactic archaeology reading the stars like cosmic scrolls. Every star in a galaxy holds secrets, chemical fingerprints in its light, precise orbital paths, even its very age acting as a timestamp of cosmic history. Together, they form an archive more detailed than any ancient manuscript, waiting to be deciphered. This is the essence of galactic archaeology, teasing out a galaxy's past not through telescopes pointed at distant collisions, but by studying the stellar survivors right in our cosmic neighborhood. Take the Milky Way's halo, where some stars orbit in bizarre, looping paths or cluster in unexpected groups. These aren't random anomalies, they're celestial breadcrumbs, tracing back to smaller galaxies our own swallowed billions of years ago. Just as archaeologists piece together human history from pottery shards and buried ruins, astronomers reconstruct galactic mergers by analyzing starlight. A star's composition reveals its birthplace. Its motion betrays whether it was born here or captured in a collision. Even the faintest, oldest stars, those nearly as ancient as the universe itself, hold clues. Their metal-poor chemistry pointing to a time before repeated mergers enriched the cosmos with heavier elements. The tools of this cosmic detective work are as precise as they are ingenious. Spectrometers break starlight into rainbows, exposing dark absorption lines that act like barcodes for elements carbon, oxygen, iron. Space telescopes like Gaia map stellar motions in 3 dimensions, revealing entire streams of stars moving in unison, remnants of long-digested galaxies. And simulations compare these observations to countless merger scenarios, reverse engineering how each stellar population arrived in its current place. What's remarkable isn't just what galactic archaeology uncovers, it's how personal these discoveries feel. When scientists identified the Gaia-Enceladus merger, they weren't just studying an event from 9 billion years ago, they were holding up a mirror to our own galaxy's violent youth. Every time you look at the night sky, some of those faint points above you might be celestial immigrants, their presence whispering of a time when the Milky Way was smaller, hungrier, and still stitching itself together from smaller pieces. This field does more than satisfy curiosity. It reshapes our understanding of galaxies as living, evolving entities, like tree rings recording years of growth, or ice cores preserving Earth's climate history. Stars encode the universe's past in their light. And as galactic archaeologists learn to read them more fluently, they're uncovering something profound. The universe doesn't just build galaxies through collisions, it remembers them one star at a time. 39th mechanism. Future mergers, the fate of the Milky Way. The Milky Way isn't just a cosmic spectator, it's a future participant in one of the universe's grandest collisions. In roughly 4 billion years, our galaxy and its neighbor, Andromeda, locked in an inescapable gravitational embrace, will slam together in a slow-motion spectacle that reshapes them both. The result, a colossal new galaxy some astronomers have playfully nicknamed Milkdromeda, a hybrid titan born from the wreckage of 2 spirals. What makes this impending merger so fascinating isn't just the scale, it's our front-row seat to the process. Supercomputer simulations reveal an almost poetic sequence. First, Andromeda's enormous disk will stretch across our skies, its spiral arms warping into surreal arcs as tidal forces take hold. Over millions of years, the galaxies will swing past each other in a series of close passes, flinging stars into dazzling tidal tails before finally recoiling and merging into a single, glowing elliptical. But here's the surprising part. despite the cosmic violence, actual stellar collisions will be vanishingly rare. The distances between stars are so vast that most will glide past each other untouched, like two swarms of fireflies passing in the night. Instead, the real drama unfolds in the gravitational reshuffling. Stars flung into new orbits, gas clouds colliding to ignite newborn stars, and the Milky Way's delicate spiral arms dissolving into a smoother, rounder shape. For life on Earth, or whatever remains of it by then, the view would be nothing short of breathtaking. Andromeda, now a looming presence in the sky, will grow larger with each passing eon, its structure distorting as it nears. During the closest passes, the night sky will shimmer with the light of 1 trillion stars, many of them strangers from the incoming galaxy. And when the merger finally settles, the familiar band of the Milky Way will be gone, replaced by a golden haze of stars orbiting in all directions. This event isn't just a distant curiosity, it's a mirror held up to countless mergers that have shaped the universe before us. By studying it, astronomers gain insights into how galaxies evolve, how elliptical giants form, and even how the cosmos itself recycles material across eons. The Milky Way's fate is a reminder: no galaxy exists in isolation. We're part of an endless celestial dance, where even the grandest structures are fleeting, destined to collide, merge, and be reborn. 40th mechanism: primordial mergers, the first cosmic collisions long before galaxies settled into their elegant spirals and stately ellipticals. The universe was a far wilder place, a cosmic free-for-all where collisions weren't just common, they were essential. In those chaotic early epochs, barely 1 billion years after the Big Bang, galaxies weren't the polished structures we see today. Instead, they were ragged, gas-rich clumps, colliding and merging with such frequency that their growth outpaced anything possible in the modern cosmos. These primordial mergers operated on a different scale entirely. With the universe still compact and dense, galaxies jostled like commuters in a crowded train, drawn together by gravity's relentless pull. But unlike today's carefully choreographed mergers, these early encounters were raw and unchecked. There were no well-defined spiral arms to distort, no orderly disks to thicken, just vast clouds of pristine gas and the first generations of stars crashing together in a frenzy of creation. The aftermath of these ancient collisions shaped everything that followed. Each merger funneled gas toward the centers of these protogalaxies, igniting furious starbursts and feeding the supermassive black holes that would one day anchor entire galactic ecosystems. The energy released in these events didn't just build galaxies, it ionized the surrounding hydrogen, helping to clear the cosmic fog that once filled the universe. In a very real sense, these early mergers didn't just assemble galaxies, they helped make the cosmos transparent. Astronomers glimpse these titanic events by staring back in time, using telescopes like Hubble and JWST to capture light that's traveled nearly 13 billion years. What they've found is astonishing: luminous, clumpy galaxies already far larger than expected, their existence only possible through rapid, repeated mergers. Some even show signs of multiple nuclei snapshots of collisions frozen in mid-process, their cores still distinct but doomed to merge. So while today's galactic mergers unfold with stately grandeur, their ancient ancestors were the true pioneers, violent, messy, and utterly transformative. Every galaxy we see around us, from the Milky Way to the distant giants at cluster centers, owes its existence to those first cosmic collisions. They were the crucible in which the universe forged its grandest structures, setting the stage for everything that followed. 41st mechanism: merger remnants, the aftermath. Even centuries after a storm passes, The landscape still tells its story: toppled trees, shifted boulders, scars etched into the earth. Galaxies are no different. Long after the fireworks of a merger fade, the transformed galaxy carries subtle yet unmistakable signs of its violent rebirth. These cosmic remnants aren't just scars, they're forensic evidence, revealing how the collision unfolded, which galaxies were involved, and what the future holds. Take the galaxy NGC 7252, nicknamed the Atoms for Peace galaxy for its looping, electron-like tidal tails. At first glance, it appears chaotic, a tangle of stars and gas with no clear structure. But look closer, and those very distortions become a timeline, the sweeping arcs of stars, their frozen snapshots of gravitational forces at work during the merger. The oddly clustered star groups near the core, likely stellar nurseries, ignited when incoming gas was compressed during the collision. Even the galaxy's irregular shape whispers secrets, betraying the angle and speed at which the two original galaxies met. Black holes, too, leave calling cards in the aftermath. A post-merger galaxy might harbor an active nucleus, its supermassive black hole still feeding on lingering gas, a last encore after the main show. Others might show twin black holes spiraling toward each other, not yet merged but close enough to warp their surroundings. These remnants help astronomers piece together the final stages of galactic unions, like finding two sets of fingerprints at a crime scene. But perhaps the most fascinating aspect of merger remnants is their longevity. While tidal tails eventually fade and starbursts quiet down, certain signatures, like unusual star motions or chemical imbalances, can persist for billions of years. Our own Milky Way's halo contains such clues: streams of stars with odd orbits or atypical metal content, each a remnant of some long-ago galactic snack. Studying these features isn't just about reconstructing the past, it's a window into galactic resilience. A post-merger galaxy isn't broken, it's reborn, its scars proof of survival. And for astronomers, every distorted shape or misplaced star cluster is like a page in an epic cosmic diary, waiting to be read. So while the universe constantly changes, it never truly forgets, and in the faintest anomalies, the grandest collisions still echo. 42nd mechanism: observational techniques decoding cosmic collisions, peering into the heart of a galactic merger, isn't as simple as pointing a telescope and snapping a photo. These cosmic events unfold across multiple dimensions: visible light, invisible gases, searing radiation, each telling a different chapter of the story. To piece together the full narrative, astronomers deploy an entire arsenal of instruments, each tuned to a different slice of the electromagnetic spectrum, like specialized translators decoding a celestial language. Radio telescopes, for instance, cut through the obscuring dust that shrouds colliding galaxies, revealing the cold molecular gas where new stars are born. The Atacama Large Millimeter Array ALMA in Chile captures these faint whispers, mapping the fuel reservoirs that power starbursts. Meanwhile, infrared observatories like the James Webb Space Telescope detect the warmth of dust itself, exposing hidden nurseries where young stars blaze behind veils of cosmic debris. But the spectacle doesn't stop there. X-ray telescopes, such as Chandra, pierce even deeper, imaging the scorching gas heated to millions of degrees by supernova shocks or the voracious appetites of black holes. In some merging galaxies, these observations unveil twin X-ray signatures, proof of paired supermassive black holes spiraling toward their eventual collision. And when it comes to the highest energy phenomena, gamma-ray detectors trace the aftermath of particle jets screaming into space at nearly light speed. Yet perhaps the most revolutionary tool isn't a telescope at all, it's supercomputer simulations. By combining data across wavelengths, researchers create dynamic models that predict how mergers unfold, testing theories against real-world observations. These digital laboratories let us rewind and fast-forward cosmic time, witnessing processes too slow for any human lifetime. Together, these techniques form a mosaic of understanding. A single snapshot in visible light might show only the graceful arcs of tidal tails, but layered with radio and X-ray data, the same merger reveals a saga of chaos and creation, gas collapsing into stars, black holes awakening, and galaxies reborn. It's a reminder that the universe doesn't give up its secrets easily, but with the right tools, even the most violent collisions become windows into cosmic evolution. 43rd mechanism, computer simulations. Virtual cosmic labs imagine reconstructing a car crash in slow motion, except instead of vehicles, you're analyzing galaxies colliding at millions of kilometers per hour, and instead of a crash test dummy, you've got a supercomputer crunching billions of data points. That's the power of modern astrophysics simulations, entire galactic mergers unfolding in meticulously crafted digital universes, where scientists can pause, rewind, and dissect every moment. These aren't just video game renderings, they're precision instruments, built on equations governing gravity, hydrodynamics, and dark matter. By feeding in known physics, astronomers let virtual galaxies collide under countless scenarios, varying angles, speeds, and compositions, then compare the results to real-world telescope observations. What emerges is nothing short of revelatory. Spiral arms twisting into tidal tails, black holes circling each other in decaying orbits, starbursts igniting in shock-compressed gas, all behaviors predicted by code before being confirmed by lenses. One groundbreaking insight from these simulations, the critical role of dark matter halos, early models treating galaxies as mere collections of visible stars failed to match observations. But once simulations included vast, invisible halos of dark matter anchoring galaxies and shaping their gravitational pull, the virtual mergers suddenly mirrored reality. It's akin to realizing air resistance matters when modeling falling feathers. What seemed like background noise turned out to be central to the story. The real magic lies in scalability. A single simulation can span billions of years in days, letting researchers witness processes too slow for human observation. Want to see the Milky Way and Andromeda merge? Supercomputers like Illustris TNG or Eagle have already run the experiment, revealing that Earth's night sky will one day blaze with newborn stars before settling into an elliptical glow. Yet simulations aren't infallible. Their accuracy hinges on the assumptions programmed in, like the ratio of gas to stars or the behavior of black hole jets. That's where the synergy with observation becomes vital. Telescopes flag anomalies in real mergers, prompting tweaks to the virtual rulebook. It's a constant dialogue between silicon and starlight, each refining the other. For astronomers, these digital labs are more than tools, they're time machines, letting them probe the universe's past and future with a keystroke. And for the rest of us, they offer something equally profound, a front-row seat to cosmic collisions we'd otherwise never live long enough to see. 44th mechanism, unsolved mysteries, the open questions. After untangling 43 intricate mechanisms behind galactic mergers, we've arrived at the frontier, the great unsolved puzzles still baffling astronomers. For all we've learned, These cosmic collisions guard secrets that defy even our most advanced simulations and telescopes. How exactly do supermassive black holes, after centuries of spiraling, finally merge into one? Why do some mergers explode with starbursts while others fade into quiet rearrangements? And perhaps most perplexing of all, does dark energy, the enigmatic force accelerating the universe's expansion, subtly steer these collisions from the shadows? Take the final moments of black hole mergers, for instance. Einstein's equations predict a violent finale, a burst of gravitational waves as the event horizons snap together, but the details remain blurry. The last few orbits before coalescence happen in a frenzy of warped spacetime, where quantum effects may clash with relativity. Current telescopes simply can't capture this microscopic drama unfolding across cosmic distances. Future detectors, like the planned Laser Interferometer Space Antenna LISA, aim to eavesdrop on these whispers of spacetime itself, potentially revealing whether black holes ring down like struck bells or vanish with a cosmic silence. Then there's the starburst puzzle. Two nearly identical galaxies can collide, yet one erupts in star birth while the other lies dormant. The difference might hinge on gas turbulence, magnetic fields, or even the timing of their collision, variables so subtle they're like trying to predict whether two storm fronts will spark a tornado or just rain. Some theorists suggest a galaxy's merger fate is written in its dark matter halo, whose invisible contours funnel gas into critical regions or disperse it entirely. Others point to supermassive black holes, whose feedback can either ignite star formation or snuff it out. Untangling this requires not just sharper telescopes, but new ways of modeling galactic chaos. And looming over everything, dark energy's shadow. As the universe expands faster, galaxies will grow isolated, their mergers becoming rare relics of a bygone era. Could this acceleration alter how collisions unfold today? It's a question without answers, yet one that reminds us galactic mergers aren't just about gravity and gas, but the universe's evolving fabric itself. These open questions aren't setbacks, they're invitations. Every mystery fuels new missions, from next-generation observatories to bold theories reimagining cosmic physics. What we've uncovered so far is staggering, but the next chapters promise revelations that could rewrite our understanding of galaxies, black holes, and the universe's deepest rhythms. The story isn't complete, it's just getting thrilling. 45th mechanism, human perspective, why mergers matter. Every atom of oxygen in your lungs, every speck of iron in your blood. These weren't just made in stars, they were forged in the furnaces of colliding galaxies. The grand dance of galactic mergers isn't some abstract spectacle happening far away. It's the reason we exist. The gold in your jewelry, the calcium in your bones, even the silicon in your smartphone. These heavy elements were cooked up in the chaos of ancient mergers, then scattered across the cosmos by stellar winds and supernova. Without these violent encounters, the universe would still be a sea of hydrogen and helium, devoid of the complexity that makes planets and life possible. Think of it this way: the Milky Way's own history is written in the stars you see overhead. Some of them are refugees from long-ago mergers, their chemical fingerprints betraying origins in other galaxies. When you gaze at the night sky, you're not just looking at distant lights, you're seeing fragments of our galaxy's past collisions, the very events that enriched it with the raw materials for Earth, and eventually us. Andromeda's impending collision with the Milky Way isn't just a future astronomical event, it's the next chapter in a story that began with the first stars and will continue long after our sun burns out. But the connection runs even deeper. Galactic mergers shaped the architecture of our cosmic neighborhood. Without them, the Milky Way might never have grown large enough to host a stable spiral disk, the kind of orderly structure that allows planetary systems like ours to exist safely for billions of years. Those violent encounters between galaxies didn't just supply ingredients, they built the kitchen where life could eventually simmer into existence. So while mergers may unfold over epochs too vast for human comprehension, their legacy is written into our very atoms. They remind us that we're not just observers of the universe, we're products of it, stardust woven together across billions of years by gravity's patient hand. Every time astronomers study a galactic collision, they're not just unraveling the fate of distant stars, they're tracing the origins of everything we know, including ourselves. The next time you hear about colliding galaxies, remember, you're not just hearing a scientific curiosity, you're listening to an echo of your own cosmic ancestry. Closing the cosmic circle, where destruction becomes creation, we've journeyed through the symphony of forces that orchestrate galactic mergers, from dark matter's invisible grasp to the supernova-fueled winds that sculpt entire galaxies. But here's the profound truth hidden in these collisions. What looks like chaos is actually the universe's most elegant recycling program. Every shattered spiral, every scattered star stream, even the ferocious glow of quasars, they're all part of a grand cycle where endings are just disguised beginnings. Consider our own Milky Way, a patchwork quilt of cosmic annexations. Those faint stellar streams wrapping around our galaxy, they're the fading echoes of dwarf galaxies devoured billions of years ago. The heavy elements in our bodies, forged in merger-triggered starbursts long before Earth existed, we're not just observers of this process, we're products of it, stardust shaped by gravitational tides we'll never feel. And the dance isn't over. When Andromeda collides with us in 4 billion years, it won't be an apocalypse, it'll be a rebirth. New stars will ignite from compressed gas, our supermassive black holes will spiral into a titanic embrace, and the resulting elliptical galaxy may one day host civilizations who will trace their origins to this very collision. The universe doesn't destroy, it reconfigures, trading one form of beauty for another. So the next time you gaze at a galaxy in a telescope, or even just glimpse the Milky Way's faint band across the night sky, remember, you're seeing a snapshot in an epic, billion-year narrative. Those tranquil spirals and serene ellipticals, they're all transient phases in an endless waltz of gravity, chance, and renewal. The cosmos refuses to stand still, and thanks to these 44 mechanisms, neither does our understanding of it. As the final notes of our exploration fade, let's not say the end. Instead, let's say, to be continued. After all, out there right now, two galaxies are drawing closer, their fates intertwining in ways that will one day rewrite the star charts. The universe is alive with motion, and the greatest discoveries, they're still waiting in the dark.